Hello. So far, we've seen a way to achieve epsilon differential privacy in a trusted curator model. And to do this, we calculated the sensitivity of the function for which we want to be function that we want to be private, and we added Laplacian noise, where the spread or approximately the variance of the noise depends on the sensitivity of the function that we are trying to protect or make it private. Now, before we move ahead and talk about an approximate notion of privacy, what I just wanted to point out one thing is that the same idea of computing the sensitivity and adding Laplacian noise also works when you are releasing as a mechanism not just a single value, but you might release a bunch of values. What do I mean by that? In this case, let us say you have some data set x, and your function that operates on this data set x might take this data set and map it to not just a single value, but a bunch of d different values. For example, let us say again in the survey example that we have been looking at, we get binary variables values from n different people, and we were interested in the average value earlier. Now, we might also be interested, let us say, in the in other functions of the binary variables, let us say the median, or let us say some quantile values, and so on and so forth. Basically, what I am trying to say is that it is the same data set, and from the same data set we compute different functions and then release a bunch of values. You can think of this as if we are releasing not a single number, but a vector, right? So, the vector is in d dimension, which means that there are d different values that you are computing from the same data set and releasing it to the public. Now, how can we make this private? Well, the idea is exactly the same. Instead of adding a one dimensional Laplacian noise, we will now add Laplacian noise with mean 0, a d dimensional 0 vector, and the sensitivity is still something like del by epsilon, where now del is defined slightly differently. Well, I should say this is del by different into I, and we will talk about this. Del is just max over all x comma x prime neighboring Now remember, my function f returns a vector. So, we are comparing two different vectors, and earlier we were just computing the absolute difference. Now, what we will do is we will compute the L1 norm between these two, right. So, L1, that is, we will compute sum over I equals 1 to d the ith component's absolute difference. Okay, and now we will add del by epsilon as the spread parameter for the Laplacian noise for each of these components. In other words, if you want to think of this as a covariance matrix, then you can multiply it by I, but maybe it's a better way to say that. Maybe I will say it this way: Laplace of 0 comma del by epsilon in all components independently of each other. What does that mean? That means that what we are doing is, we are sampling a noise value for each component from a distribution which is Laplacian with 0 mean, and del by epsilon as the spread parameter, where del is defined as the L1 sensitivity of the function that we are trying to compute. Now, one can show that this is also epsilon differentially private when you are releasing f, which is a vector valued function. So, that is one point I just wanted to make it clear, that it's not just that we are releasing, we have to release just a single value, we might release multiple values, and the idea is, if you are releasing multiple values, somehow information can get leaked in different ways, and so you will have to protect it together. So, naturally the sensitivity is going to be larger because you are protecting d different components. Okay, good. So that's one point I wanted to say. So now let's talk about slightly different variant of differential privacy, which is what is called as approximate differential privacy. DP for differential privacy, and let me put down the definition and then we will talk about what it means. We will say some mechanism M as usual, and let me say what is this mechanism. Well, it takes n different values and maps it to some output, which can be, let's say, 0 or 1 depending on, or real number depending on your problem at hand, is epsilon delta approximately differentially private, or sometimes this word approximately is not used. We will just say epsilon delta differentially private, and that means we are talking about approximate differential privacy. If for all neighboring x and x prime in Xn and all y set S subset of y, we have the following criteria that gets satisfied. Let me put it in a different color. The probability that m of x subset of S is less than or equal to m of x, belongs to S, is less than or equal to e to the epsilon probability that m of x prime belongs to S. So far it is the same, but then because it is an approximate notion, we will add plus delta. So, so this is the definition, right? So, given an epsilon and delta, we will say that a mechanism M is approximately epsilon delta differentially private if for all neighboring data sets x and x prime, the probability of m of x belongs to some subset in the output S is at most e to the epsilon times the probability of the same the mechanism giving out the value in the same subset for a neighboring data set plus delta. So, in other words, well, of course, if delta is 0, this means that it is exactly the same as the definition of differential privacy that we know already, but this delta can be thought of as giving us some leeway, right. So, there might be some low probability events or some subsets S where the epsilon differential privacy property may not hold, right. So, and we are saying that if that is a very small probability event, then where that is where the probability is at most delta, we are still safe, right. So, we are not, in other words, we are not enforcing that the epsilon differential privacy property, which is a very strict requirement that no matter what the subset S is in the output, we need the property to be satisfied. The ratio should be at most e to the epsilon, but now we are saying that, well, there is some wiggle room of delta for some subsets S, right. So, that's why it is called approximate differential privacy, because you are achieving epsilon. So, one can show that if this property is true, then you are achieving epsilon differential privacy for most of the subsets S, right. So, with very high probability, you are achieving epsilon differential privacy, so to say. Okay, so two questions. One is, how do we achieve this? Well, one obvious way to achieve this would be to use the Laplace mechanism itself, right. So, because the Laplace mechanism satisfies a stronger notion of epsilon differential privacy, which means that with delta equals 0, you get epsilon comma 0 differential privacy if you use the Laplace mechanism. But the whole idea is that because we are relaxing this a little bit, maybe that's a different way to achieve this, and by doing that different way of achieving this, can we gain something in terms of, let's say, utility, right. So, that's the bigger question, bigger hope that we have, and the answer is yes. And again, we won't go into the proofs of this in this course, but I would at least like to tell you how to achieve this and what does that essentially give us, right. So, to achieve this, use the what I am going to call as the Gaussian mechanism. So, instead of the Laplacian mechanism, we can use a slightly relaxed mechanism called the Gaussian mechanism, where we can achieve this. And how exactly do we achieve that? Well, again I am going to give you the mechanism itself. We won't prove that this is epsilon delta in this course, but it is not too hard to prove also. So, we will add Gaussian noise, as simple as that, right. So, instead of the Laplacian noise, we will add Gaussian noise to the function that we are trying to compute. And what exactly is this Gaussian noise? Well, Gaussian noise is typically indicated as n for normal distribution, same as Gaussian distribution, with mean 0 and variance ln of 1 by delta del squared by epsilon square. So, it's a slightly different noise that you are adding. So if you are aware, the Laplacian noise is, PDF looks something like this. Now, the Gaussian is a more common, well-known PDF. It looks like this, right. So, it falls faster than the Laplacian noise. Okay. So, what are we doing here? We are saying that if I give you a specific epsilon and delta, then the noise that you should add is of course 0 mean, and the delta plays a role here in the variance, right. So, so there are two deltas here. So, this is the delta for the epsilon delta differential privacy. This is the sensitivity. I am not going to call this as delta, I will call this as the sensitivity. So, this is the sensitivity squared by epsilon squared. Now, one can show that if you do this, then we can achieve epsilon delta differential privacy. Now, like how for the Laplacian case, when you have multiple outputs, we would add Laplacian noise to each of these components separately, and the sensitivity was calculated as an L1 sensitivity, the L1 norm difference between the outputs of the neighboring data sets. Here what we will do is, for high dimensional outputs, the noise that you will add will be 0 mean ln 1 by delta. It's the same thing, del squared by epsilon squared, but this will be del 2 squared, right. So, and that just means this is the L2 sensitivity, right. So, instead of the L1 norm, we are looking at L2 norm. So, basically del 2 can be defined as max over x comma x prime neighboring f of x minus f of x prime is L2 norm. What is L2 norm? Well, L2 norm is sum over I equals 1 to d f of x minus f of x prime's ith component square, and then you take the square root, right. So, this is the standard Euclidean norm, the way we measure distance between any two points in space in Euclidean geometry. This is just that L2 norm. So, we have L2 squared as a sensitivity squared divided by epsilon squared is what is the noise that you should add to achieve epsilon delta differential privacy. Now, the question is, why are we doing this, right. So, what do we gain by adding Gaussian noise? Of course, what we lose is that from a epsilon differential privacy, we have lost the strong notion of epsilon differential privacy. We only have an approximate notion, right. So, that is there is some set S in the output space of some probability for which our epsilon differential privacy guarantee may not hold. That is what this delta is, allowing us, right. So, there is some low probability event which if it happens, we cannot guarantee, right. So, in fact we can perhaps that means that by looking at the output, maybe if that event happens, we will be able to figure out whether x generated that output or x prime generated that output. The difference is larger there, right. So, and so we will be able to figure out, but such an output happens with very, very low probability, and so we are kind of okay with that, right. So, for most of the times, if you draw noise from Gaussian distribution, you are not going to see something where you will not have epsilon differential privacy. For most of the time, you will have strict epsilon differential privacy. For very rare events, you will not have. So, nevertheless, we have lost something there, right. So, if the rare event happens, then yes, we do not have necessarily epsilon differential privacy. But what have we gained, right? So, we should have gained something, otherwise we would not do this. And what we gain again is, so we gain in terms of, and this should be easy to guess by now, in terms of utility, and the way we will describe that is as follows. Well, if you think of sensitivity itself, right? So, how much what is the sensitivity that we have? So, for the Laplacian noise, if just to give an example, right. So, we were adding Laplace of 0 comma del by epsilon, which is like Laplace of 0 comma. So, if each of the component was something like 1 by n sensitive, when I say 1 by n, you have n different binary variables, and if this binary variable, so then for neighboring data sets, it cannot change. Let us say something like a mean cannot change by more than 1 by n, and let us say if each of the components had that 1 by n kind of a sensitivity, then the L1 norm is adding up the maximum difference in each of the components. So, there are d different outputs, and each component is 1 by n sensitive. So, the total noise that will essentially end up adding is of the order d by n epsilon. This epsilon is already there. This d by n comes because it is just sum over I, the absolute difference between f of xi, the ith component, which is all 1 by n, and I equals 1 to d, and so this is d by n, right. So, this is d by n epsilon. That is the Laplacian case. Now, in the Gaussian case, what will happen is that we will gain something. In the Gaussian case, what we will end up adding is n of 0 comma, if you do the calculation for something very similar like this, we will end up getting something like square root of d log 1 by delta by n epsilon. So, when I say that, so this is the standard deviation here, right. So, so roughly the spread corresponds to the standard deviation. Essentially, what the key thing to note is that the n epsilon in the denominator is the same, that is the same. So, then we are kind of trying to compare how much noise that we add by looking at the numerator, and if you look at the numerator, here it is of the order d, the spread that you add is of the order d, which means that if there are d components, d things that I am releasing as output to the public, then the noise kind of adds up linearly, whereas here it is only square root of d. Of course, there is an extra log 1 by delta that you will have to suffer, but then that is just log, right. So, okay, so let me just be consistent here. When I say log, it is typically ln, which is just to the base, log to the base e, but that does not matter, that is just a constant which will differ. Even if I put log, the order will remain the same, but the important thing is that this is of square root of t, right. So, if we are comparing in the same scale, it has to be either compared as variance or standard deviation, right. So, if you fix that scale and see how much noise do you end up adding in a Laplace mechanism versus how much noise you end up adding in a Gaussian mechanism. So, there is quadratically lesser amount of noise in terms of the number of components or number of output that you are releasing. Instead of d, this is just square root of d. Well, there is an extra factor that you will have to suffer not exactly square root of d, slightly more than square root of d, and that slight extra is ln of 1 by delta. But because it's ln, if delta is, even if delta is small, the logarithm is going to make that ln of 1 by delta not too large, right? So, so what essentially you're doing is, you can think of it roughly as some constant times square root of d versus d, right? So, and when d is large, when the number of output that you are releasing is large, then you will have to add quadratically more amount of noise to maintain epsilon differential privacy, but then you can get away with much less noise if you are happy to settle for epsilon delta differential privacy. Now, because you are adding less amount of noise in the Gaussian mechanism, well, basically you are corrupting the output and giving it to the user. Now, the amount of corruption is the noise, right? So, and because you are adding less amount of noise, the actual value that you really want to give to the user, but you cannot because of privacy issues, is getting corrupted lesser, and so you will have higher utility, right? So the Gaussian noise helps you achieve higher utility because the amount of noise that you add is lower. Of course, by this we can try to analyze, we can work out what is the exact utility, which I am not really doing here, but the point that I want to make is, because it's Gaussian noise, you will end up adding less amount of noise. And the fundamental reason why this works is because, of the L1 versus L2 ways of measuring things. But again, let's not worry about that too much in this course. The main takeaway here is that we are letting go of some amount of privacy for certain rare outputs. That's the delta part. And once you are okay with that, what you gain is, for the other things where you do have epsilon differential privacy, your utility is quadratically better than the utility that you would have gotten had you just used blindly a Laplace mechanism, right? So, Laplace mechanism is epsilon 0 differentially private, but then if you allow a little bit of leeway in terms of not caring about privacy for rare events, then your utility becomes quadratically better. So, that is the approximate differential privacy's advantage. That is the first advantage of approximate differential privacy. So, what we will also see are some very interesting properties of approximate differential privacy mechanisms, and that is why this is quite popular, and we will later see in the future videos that how we can make use of these properties that we are going to see now to make machine learning algorithms also private, right? So, but the reason why we are talking about this is eventually we will get to machine learning algorithms and make them private, and for that we will use properties that I am going to talk about now. So, what are these properties? Let us see them. Okay. So, properties of I am going to call this ADP for approximate differential privacy. So, the first property, and there are several properties, we'll talk about some important properties that are pretty much needed from a machine learning context later on. The first property is called as post processing. So, what does this mean? So, let us say we have some mechanism with us, say M is a mechanism, is epsilon delta differentially private. So, I am not saying approximate because the delta means that it is approximate differentially private. Now, let us say, what does this mean? This means that there is some input x and which is some data set, and I do some computation on this data set, I release something via the mechanism M, and I have added Gaussian noise appropriately so that I can achieve epsilon delta differential privacy. Now, the world or an adversary sitting in the world is looking at this value that M releases. And we are guaranteed that, well, M has this nice property that by looking at the output of M, I cannot figure out whether X generated it or X prime generated it up to the delta delta probability. Now, if I do some post processing on the output that M releases, it should not suddenly become less private, right? So, let us say you added noise and gave me a vector, and now I know that this vector has this nice property of epsilon delta differential privacy. Now, let us say I input this vector to some other function, and now this vector is post processed to become something else, and suddenly that's just by making this post processing, I should not lose any privacy guarantee, right? So, which means that if there is some other function f and then I am composing f with m, right. So, this is a composition symbol. Basically, I am applying f after I apply m. That should also be epsilon delta differentially private. So, which means that this is a natural thing, but this is important to state it, because it should not become the case that I am only protecting what I am releasing, but not some functions of it, right. So, this is saying that if you are doing approximate differential privacy, you are not only protecting what you are releasing, but all functions of that as well. I cannot do some, let us say you give me a vector, and then let us say I cannot add the values of that vector, and suddenly I get to know more information about the input. That cannot happen, right. So, that's a good property to have, and that is indeed satisfied by epsilon delta differential privacy. The second thing is another interesting property, and this will become very critical later on for privacy in machine learning applications, especially when you are training using gradient descents and so on, is the property of composition. And there are two different variants of it. There is a basic variant and an advanced variant. We will just look at the basic variant, and I will make a note or a comment about the advanced variant. So, let us say we have M1, M2 dot Mk. There are k different mechanisms, and are all epsilon delta differentially private. Right. So, you have k different mechanisms which operate on a data, and then they are releasing their own stuff, and then all of them are epsilon delta differentially private. Now, well, essentially what does this mean? This means that you are kind of leaking information up to epsilon delta differential privacy via each of these mechanisms. And now, if a user has access to k such mechanisms output, how much is the combined privacy guarantee on the data set, right? So, essentially I am a data set, and then I have a data set, and then I give my data set to k different parties, and then they are doing their own things, and then they are all releasing epsilon delta differentially private quantities to the world, and then there is an adversary sitting in the world who has access to all these k different outputs from k different parties, each of which is epsilon delta differentially private. Now, how private is my data set, right? Now, because you are leaking epsilon delta information from each of these mechanisms, it cannot be the case that you have leaked only epsilon delta for the mechanism that puts together all these k things. The interesting thing is that the basic composition theorem says that the combined thing, right. So, an adversary who has access to output of all these mechanisms still has something like k epsilon k delta differential privacy. What does this mean? This means that the privacy has become worse by a factor of k. That's a natural thing to expect, right. So, that's a straightforward thing to expect, because each of these mechanisms is is leaking something like epsilon, and there are k such mechanisms. So, it is natural to expect that the total leak is k times epsilon. Similarly, each one is delta approximately differentially private. So, you are it might be different, output sets of probability of delta where you are failing, and so when you are putting everything together, a weak union bound kind of would say that there are k different portions of the output space where you are perhaps not epsilon differentially private. So and each of these k has probability delta, so put together you lose k delta, right. So I mean your approximation becomes worse. Now this is the basic thing, and I mean for the curious uh, you know uh, participant who is watching the video, you can try to prove this yourself. It's very, I mean, assuming that each of M1 to Mk is epsilon delta differentially private, it's not actually too hard to prove that the combined mechanism that releases all these together is k delta, k epsilon k delta differentially private. There is an advanced version. Now you can take advantages of the fact that this is a Gaussian, and this is important that this is a Gaussian distribution where we are adding noise from, and you can prove a complicated but an interesting result that the combined mechanism is actually something like epsilon k square root of k log 1 by delta prime plus epsilon e to the epsilon minus 1 comma k delta plus delta prime differentially private. Yeah, so it's a mouthful to read this out, but the idea is that you can get better combined better combined privacy and approximation if you do a more careful analysis, right. So just to point this out, this was k epsilon, so this is epsilon times something like square root of k. Of course, there is another factor of log 1 by delta prime, and you can optimize for delta prime and so on. But the interesting thing is that the k has gone out and you only have square root of k. And why is this important? And we'll talk about this later when we are talking a bit about private machine learning. Just to give an example, you can think of it as running if you know the gradient descent, which is a standard workhorse algorithm for machine learning. Now you can think of releasing the gradients at every step while performing gradient descent, and which means that at every step you are leaking some information, and after making k gradient steps you would have lost k epsilon in the usual way if you are adding let's say Laplacian noise. But now if you add Gaussian noise, then what this is saying is that, well, you would lose something like square root of k epsilon only, which means that you can be private for more number of iterations, and the more number of iterations, the better your quality of solution in a machine learning context is going to be. We'll again come back to this when we talk about privacy in machine learning, but just to give an idea for you that as you maybe think of this as a process where you are keeping on releasing different outputs, and you want to preserve privacy in a combined fashion, and because you want to release out many such outputs, you want to run this algorithm for many rounds, let's say gradient descent, you want to make sure that at every round you don't lose too much, and by doing a Gaussian noise you can actually achieve square root of k times epsilon, which you cannot do if you are using a Laplace mechanism, by the way, right. So you have to use a Gaussian mechanism, and you have to settle for approximate differential privacy, but because you have settled for approximate differential privacy, you gain in terms of the privacy factor by a quadratic factor, right. So it will be square root of k epsilon as opposed to k epsilon, which is the basic thing, right. So both of these are true for the Gaussian mechanism. The basic is easy to prove, the advanced is hard to prove. Nevertheless, both are true, whereas only the basic is true for a Laplace mechanism. The advanced is not true. So if we want better privacy for a longer period of time, then we have to settle for Gaussian mechanism or an approximate differential privacy. So, so with that we have concluded broadly the two interesting aspects of privacy. One is epsilon differential privacy, the other is what we saw just now, which is the approximate epsilon delta differential privacy. we will see applications of this in machine learning as we go along. But the next thing that we will see is trying to apply privacy in a slightly different context, especially in a buyer-seller kind of a context. And we'll talk about that, and then after that we'll start talking about privacy in machine learning using all the techniques that we have learned here. Thank you.